In this video, we'll do rocket science. We will derive two rocket equations. There is a rocket with a fuel in it. Mass m includes the mass of the rocket and mass of the fuel. There are engineers on the surface of the Earth. They are using their own XY axis. Let's just say this frame, XY axis, stationary frame A. They are measuring the speed of the rocket from the frame A, and the speed of the rocket is v. In order for the rocket to accelerate, they need to push fuel out of the rocket. This is called the thrust. The velocity of the fuel is u, measured by the stationary frame A. And the new velocity of the rocket is v plus dv. The new mass of the rocket is m plus dm. Notice that dm is change in mass. Therefore, it could be either positive or negative. In this example, dm is negative, since the mass of the rocket decreases. U is the velocity of the fuel measured by the stationary frame A. Thrust is happening between the fuel and the rocket. Therefore, it's good to have a moving frame, and we measure the velocity of the rocket from this moving frame. So let's just say this moving frame is B. This moving frame is moving at the same velocity as the velocity of the fuel. So we are looking at the rocket from the perspective of the fuel. Let's just say the new velocity of the rocket is v relative. V relative is relative velocity of the rocket measured by the moving frame B. So V relative is the velocity of the rocket, v plus dv, minus velocity of the fuel, u. In order to understand the v relative, let's use the numbers. New velocity of the rocket is, let's just say 100 meters per second. Velocity of the fuel is negative 20 meters per second. Then v relative is 100 minus negative 20, which is positive 120 meters per second. That is a relative velocity of the rocket measured from the moving frame B. In order to make our calculation exact, let's take time duration dt, and it approaches 0. Then increase in velocity dv also approaches 0. So relative velocity is equal to v minus u, velocity of the rocket minus velocity of the fuel. We can ignore the increase in velocity dv. Let's use the total momentum conservation. Momentum of the rocket before thrust is m times v. Momentum of the fuel after thrust is negative dm times u. Keep this in mind that dm is a change in mass, which is negative. So in order to find the mass of the fuel, we need to have a negative dm. Momentum of the rocket after thrust is m plus dm times v plus dv. Let's rewrite it and distribute to m. So mv, and then m times dv, and dm. We don't distribute the dm because it's more convenient. Okay, find the same term and we cross them out. Left hand side becomes 0, and right hand side we factor dm out, and then v plus dv minus u. And then we add mv. Therefore, we have this expression and equation. We copy down, and then we divide both sides by the time duration dt. As time duration dt approaches 0, dv, increase in velocity, is also approaching 0. So we can ignore dv, and we have the first rocket equation. dv over dt is the definition of acceleration. So this is the first rocket equation. Let's check the validity of positive and negative signs in this equation. Since the rocket loses the mass of a fuel, so dm over dt is negative. And v minus u, that is positive. And we can say v relative, and then ma, so this is negative, this is positive, mass is positive, so acceleration should be positive. The meaning of the first rocket equation is like this. The rocket loses the mass of the fuel. Instead, it gains acceleration. So this is the first rocket equation. We can use v minus u, velocity of the rocket, minus velocity of the fuel, or we can use a relative velocity, v relative. The first rocket equation is corresponding to the Newton's law, F equals ma. The left-hand side of the equation is corresponding to the force. So this special force is called thrust. And we can also define the new term, r, that is negative dm over dt. This is the mass rate of fuel consumption. This is the amount of mass that rocket loses per second. Now let's derive the second equation. We write out the first rocket equation without the time duration dt. We divide both sides by m. and we integrate both sides. Notice that we have 1 over m times dm, and we integrate it. Antiderivative of 1 over m equals ln over m. We plug in the upper limit and the lower limit into ln of m. Right hand side, it is simply upper limit minus lower limit. Since the final mass is less than the initial mass, we can switch final mass and the initial mass in the equation. So V relative is V minus U. And this is the second rocket equation. We successfully derived 2 rocket equations.